Look at a modern suspension bridge, and you are looking at thousands of tons of concrete and steel hanging in midair. Holding all of that massive weight up is a single invisible force. That force is tension. It is the mechanical action of pulling or stretching matter apart, transmitted straight down the axis of an object like a cable or a rope. If you zoom in close enough, tension is a literal microscopic tug-of-war. Iron and carbon atoms are desperately trying to maintain their lattice structure, holding their equilibrium against the external load pulling them apart. If you release that external load, an atomic restoring force takes over. It pulls the atoms back to their resting state, snapping the cable back to its original length. To build the modern world, engineers cannot rely on guesswork. They need to know the exact mathematical limit those atoms can survive before they tear apart. This diagram outlines the setup for a uniaxial tensile test. It is a standardized laboratory method used to forcefully stretch a piece of material until it breaks. An actuator applies a vertical pulling load directly to a clamped specimen. As the machine applies the pulling force, instruments called extensometers, clamped directly onto the metal, measure the precise physical elongation or strain of the material. By artificially ripping matter apart and logging the exact forces required to do it, we map a material's absolute limits of survival. The result is the stress-strain curve. This graph maps our material under tension. Notice the steep straight line from the origin, the elastic phase. Here, if you drop the load, it springs back perfectly. But as force increases, we pass the proportional limit and hit the yield point, marked Y. The yield strength is the exact threshold where the material stops bouncing back. It loses its elasticity and takes on a permanent set, a process called plastic deformation. Urgent. Down at the atomic level, the crystalline grains of the metal are being forced past their structural limits. They violently slip, sliding over one another and locking into new, permanently deformed positions. Even though the cable hasn't snapped into two pieces, passing the yield point means its structural integrity is dead. It has already failed. This 3D chart tracks the material's fight to survive. In this plastic deformation region, the material begins strain hardening. It takes increasing amounts of force to keep stretching it, right up until it reaches the absolute crest of the curve, its ultimate tensile strength. Look at step 4 in this diagram. After hitting ultimate strength, the material begins necking. A localized thinning forms, drastically shrinking the cross-sectional area. Because that neck is so thin, stress concentrates entirely in one spot, rapidly accelerating toward fracture. Necking is matter in its final, desperate phase. It is a stark visual warning of impending total collapse. Then comes the fracture point. The atomic bonds completely sever, releasing their stored kinetic energy in a violent snap. This diagram illustrates toughness, measured by calculating the total area beneath the curve. This blue section shows the energy a ductile material absorbed before breaking. Compare that to the steep gray area for brittle materials like concrete. They absorb little energy and fail almost immediately. Every material has a unique anatomy of failure. Engineers must select structural materials based strictly on these specific, mathematically proven limits. Out in the real world, this laboratory data keeps the public safe through the factor of safety. Engineers use a material's yield strength to ensure that everyday operational loads never leave the elastic zone. We can even weaponize tension to our advantage. This photo shows the Tacoma Narrows bridge deck twisting violently just before it collapsed. It remains a sobering reminder of what happens when dynamic, real-world loads, like wind and vibration, overwhelm a structure's tensile limits. Tension is not a hazard we can ignore. When it is accurately mapped and precisely controlled, it becomes the backbone of modern structural design. You can see this mastery in this archival photo of the Golden Gate Bridge. Massive, sweeping cables are held entirely in tension, effortlessly transferring the immense weight of the deck across vast distances to the vertical towers. But tension is only half of the physical equation. Every pound of pulling force suspended in those cables must be counteracted by an equal force pushing down. Awe-inspiring conclusion. Every enduring piece of infrastructure exists in fragile equilibrium, caught perfectly between the upward pull of tension and the crushing downward force of compression.